Somewhere in the constellation Scutum, hidden behind a wall of interstellar dust, sits a number that gets repeated in almost every space video on this platform. 2,150. That's how many suns it would take to match the radius of Stephenson 218, humanity's reigning largest star. You've seen the size comparisons. You've seen the thumbnails calling it a monster, a titan, undisputed. That number is quietly falling apart, and almost nobody explains why. Start small. Earth, nearly 8,000 miles across. Tiny. The sun swallows it whole, over 1 million times over. Still, in the universe, the sun is nothing special, barely average. Now meet Rigel, a blue supergiant, burning hot and blue-white, with a radius near 79 times the sun's. Already, Earth is a rounding error. Meet Betelgeuse next, a red supergiant, radius near 887 times the sun's. Swap it in for our star, and its surface reaches almost to Jupiter's orbit. Every rocky planet inside, gone before the light even arrives. Betelgeuse is famous. Betelgeuse is enormous. Betelgeuse is not even close to the largest star we know. Now, go bigger. Stephenson 218. Discovered almost by accident in 1990, buried inside a survey of a star cluster 19,000 light-years away. For decades, it sat quietly in the data, unnoticed. In 2012, astronomers combined its luminosity, 440,000 times the sun's, with a surface temperature of just 3,200 Kelvin, cold for a star. Run that through the Stefan-Boltzmann law, and the radius comes out at 2,150 solar radii. Put it where the sun sits and its surface pushes past Saturn, 10 astronomical units out. The gas giant, swallowed whole. Stand on an inner moon of that same system, and the entire sky ahead of you is just one wall of dim reddish fire, stretching from horizon to horizon for over a decade. That made Stephenson 218 the largest star ever measured. The numbers spread everywhere. Documentaries, thumbnails, size comparison videos, stacking star after star until Stephenson 218 stood alone at the top. Here's the part that never makes the thumbnail. Nobody points a telescope at Stephenson 218 and simply sees its edge. That radius is calculated, not observed. It's built from two much shakier numbers: how far away the star actually is and how bright it truly burns. For nearby stars, astronomers measure distance through parallax, watch a star appear to shift slightly against the background sky as Earth swings around the sun, and triangulate the distance from that shift. It's simple geometry. But past a few thousand light years, the shift becomes too small to detect reliably. Stephenson 218 sits 19,000 light years out, far beyond that comfortable range. Its distance has to be inferred indirectly through the motion and position of a nearby star cluster. And that's where it gets shaky. Stephenson 218 moves through space at 89 kilometers per second. The cluster it supposedly belongs to moves at over 109. That mismatch has left some researchers doubting it's even a member. If it isn't, the distance used to calculate its size may be wrong entirely. Distance uncertainty alone already exceeds 50%. Its luminosity has been quoted anywhere from 90,000 to 630,000 suns. Not a small margin, a canyon. This has happened before to a different star. Scutum held the largest star title for years, at an estimated 1,708 solar radii. Then the Gaia spacecraft refined its parallax. The true distance came out smaller than assumed. Smaller distance, lower luminosity, smaller star. Scutum's radius dropped to around 755 solar radii, more than halved without the star itself changing at all. Scutum wasn't alone. VY Canis Majoris held its own version of the crown years earlier, with radius estimates that once ran past 2,000 solar radii before later work pulled it back down closer to 1400. Almost every largest star claim of the last 2 decades has shrunk on revision. None of them has grown. The same fragile math sits underneath Stephenson 2.18, and 2,150 solar radii doesn't just sit at the edge of what's possible, it blows past it. Physics sets a rough ceiling here, known as the Humphreys-Davidson limit. Push a red supergiant's luminosity too high, and radiation pressure starts shredding its outer layers faster than the star can hold onto them. Somewhere near 1500 solar radii, that ceiling kicks in. Stephenson 2.18's official number sits 450 radii above it. Red supergiants don't even have a clean edge to measure. Thick shells of dust surround them, so dense that telescopes struggle to tell where the star ends and the cloud begins. That's why a star's outer glow can look, from Earth, far bigger than the actual surface underneath it. So the crown started slipping. For years, the leading rival was WOH-G64, a red supergiant 160,000 light-years away in a neighbouring galaxy. Its radius was around 1,500 suns, large enough to challenge Stephenson 2.18 directly. Then, in 2024, astronomers caught it changing. Not on paper, in reality. Its outer envelope stripped away, its surface temperature climbing from 3,200 Kelvin to almost 4,700. WOH-G64 didn't get remeasured smaller. It got physically smaller, shrinking toward roughly 800 solar radii as it transformed into a yellow hypergiant. A star losing its size in real time, while astronomers watched. The newest name in the race is RSGC-1F01, 22,000 light-years out, buried inside a cluster so choked with dust it stays invisible to ordinary optical telescopes. Its radius is somewhere between 1,450 and 1,530 solar radii, close enough to Stephenson 2.18's own uncertain numbers that calling either one the definitive largest star stops being a fact. It becomes an argument. And size isn't the same contest as mass. Stephenson 2.18 is enormous in radius, but far from the most massive star known. A bloated, thin-shelled giant can weigh less than a compact blue supergiant a fraction of its width. Bigger doesn't mean heavier. The universe keeps those two crowns separate, even when comment sections don't. None of this is academic trivia. These numbers decide how astronomers picture the star's final act. A slightly smaller Stephenson 2.18 collapses differently than a slightly larger one. Get the radius wrong, and the predicted supernova, the predicted remnant, the whole ending changes with it. Every figure in this race depends on assumptions no one can fully verify from thousands of light years away. Shift the distance by a few percent, change the dust model, question the cluster membership, the ranking flips. Stephenson 2.18 might still hold the title. It might not. There's a deeper reason a bigger one might already be sitting out there, unfound. Every red supergiant on this list was found because its light was bright enough and its dust thin enough to reach our telescopes at all. The most extreme candidates, the ones buried behind the thickest dust or sitting farthest across the galaxy, are exactly the ones current surveys are worst at catching. The record isn't just uncertain, it's incomplete by design. Somewhere past that dust, past the limits of what current telescopes can resolve, there could already be a star that beats every name on this list, waiting